So now I'm going to define, this quantum field theory on this non-commutative spacetime. And right. So the Moyal-Weiss spacetime, I showed it to you now many times. X hat mu is the commutator is equal to I theta mu nu. And for that, there exists a representation, which means, a map between the algebra and on the Hilbert space. So as operators on the Hilbert space, a dense domain and the Hilbert space, let's call it L2R2. And you can define it in the way that x0 and x2 act as multiplication operators with a certain constant, right? The kappa A, and x1 and x3 as derivatives with respect to S. Okay, so that exactly this commutation relations are satisfied. Now, how do you realize the quantum field on the non-commutative Minkowski spacetime? It is done by tensor product. You take the tensor product of this coordinate space, this new, non-commutative Moyal-Weiss spacetime, and you tensor it to the Fock space. So basically, you take this field, you take the operators A, and you tensor to them this exponential operator e to the IP x hat, where the x hats here are the coordinates, and here you have the sum. So I always so what in physics what we like to do is the Einstein sum convention, which means basically I sum over this, right? M goes from 0 to 4 in our case, 3, sorry. So we have 4 dimensions. And sometimes instead of writing p mu x mu, we just write px, because with that is understood that we mean that if we wanted to write the vectors, then we would write the vector side. Okay, this is sort of a notational issue. But basically all you do is you tensor this representation space of the Moyal-Weiss space by this Fock space. And the problem here, actually, okay, then you have a quantum field theory on non-commutative Minkowski spacetime, but there is a real problem. The problem is you lose this causality condition that I was telling you about, that the field phi would commutate with the field phi prime if they're space-like separated. And that was sort of a real setback in that. So because in a sense it doesn't make a lot of sense to do quantum field theory, on this high level of energy, which should be relativistic, and lose causality and locality, which are exactly the things that make the theory relativistic. Of course, you can do non-commutative, non-relativistic quantum field theory, but this is not what we were interested in the first place. Now, given a skew-symmetric matrix theta, one can construct a unitary operator phi theta such that it takes, oh, sorry, I don't know what happened here. It takes the tensor product V and V of H to V of H, okay, to this Fock space, to this many particle space. And it is done by basically doing the following. So you take these tensor A's, which were e to the I p x hat tensor A of P, and here the conjugated one. And right, and then you take the unit, you perform a unitary transformation, which takes you from that guy to that guy, where P is the momentum operator with respect to the quantum field theory. And it can be written as d3p divided by 2 omega p, p mu, a star p a p, where p mu is omega p and I think there's a nice number, and p vector. Okay, so this is the momentum operator, which basically tells you the moment. So if you apply that to some operator A, it tells you the momentum of that operator. And now, since we defined, this tensor product, this unitary operator that took us from the tensor product to the usual Hilbert space, now we have something that looks like the old one. And the question is why to do that at all will be answered in the following slide. So Gandalf, Lechner, and Harald Grosse constructed a map from a set of wedges to a set of skew-symmetric matrices, Q or thetas. Okay, so in a sense, what they did this construction, they mapped by a unitary operator these weird non-commutative Minkowski space operators to something that we can work with. And then what they discovered was that there is a map between the skew-symmetric matrices and wedges. And wedges are basically, so a standard wedge, the right wedge is this whole thing, okay? Sorry. So that is the right wedge. Basically, x0 is less equal than x1. And the causal complement of that is basically this other wedge here, the left wedge. And now what they could show by relating the non-commutative fields to these wedge fields is that there is still a sort of locality hidden in these fields, which is called the wedge locality, which is a bit weaker than the pointwise locality. So pointwise locality basically tells you if 2 points are causally separated, this is equal to 0. Wedge locality tells you if it's located in this wedge, okay, in the whole wedge, and this in the whole wedge, then they commute. So in a sense, there was a resurrection or restoration of locality, which made these models very interesting again. Now, then it was recognized by Buchholz and Summers, and then later by Buchholz, Summers, and Lechner, was formulated in a very rigorous way, that these Gandalf, Lechner, Harald Grosse fields, so the Grosse-Lechner fields, are connected to the Riefel deformation, okay? And they connected it by something called the warped convolutions. And for the rest of the talk, I will concentrate on that. Not on this, but on the warped convolutions itself. So the definition here is the following. Let theta be a skew-symmetric matrix on Rd, then the warped convolution A theta of A belonging to a certain subalgebra, forget about that in the moment, it's not that important, is given on a vector by the following formula. Okay, so you take a unitary operator, u of theta x, u of minus theta x, you take the adjoint action with respect to this operator A. Yes, sorry, is there any question? Yes? Okay. So you take this, the deformation of this operator A, the warp convolution, so the warp deformation of this of an operator A is given by the adjoint action of u of theta x, u of minus theta x, and then you multiply that with u of y and integrate over e to the minus xy. This corresponds to taking the spectral representation of an operator u, or the generator of the operator u, doing the adjoint action, and then taking the spectral measure integral over it. U of theta x is basically just a unitary operator. So take some self-adjoint operators epsilon y mu that commute among its own components. Then you can define a unitary operator u by taking the exponentiation of that, right? And then also what happens is that u of a times u of b is equal to u of a plus b. That's why it is, in a sense, an action of Rn for a and b being elements of Rn, right? Okay, what does that mean? Let me do a specific calculation to show you. Let's deform the creation operator, or the annihilation operator, A. So I take the spectral integral. The spectral integral basically, so if you have the spectral integral for a self-adjoint operator A, or let's say X, if it is sort of the integral representation of this operator. Basically it means, so of lambda, basically it means, for example, I want to take x squared. I don't know how to take x squared because this is an operator, okay? If I can prove it's a self-adjoint operator, there's the spectral theorem that tells me basically I can represent it by taking this operator projection valued measure, lambda, and doing it like this, lambda squared. Now, how to calculate with it, that's where these limits and cutoff functions come into place. So this chi, I'm sorry I didn't mention it, it's just a cutoff function to make this oscillatory integral well defined. And now I take the adjoint action of u of theta x, where u of theta x is given by I to the power of theta x times p. Okay, I take the momentum operator. I know that the momentum operator in the commutator with a of p is minus p a of p. And so the adjoint action, a of p, u of minus theta x, is basically, so you can, there are many ways to calculate it. You can do the Baker-Campbell-Hausdorff formula. You can do it by, by terms. Basically what you will get then is a of p plus the commutator of, theta x with p, a of p plus the commutator squared divided by 2 factorial, p hat, a of p, and so on, right? And since the commutator of p with a of p is p a of p, so just the momentum of this particle, and p of p is a of p, this gives you p square a of p, a of p, and then you notice, oh, this is nothing else than the exponent of e to the I theta x p a of p, which is exactly what happens here. Sorry, it is a minus. Here there is a minus, right? So this is minus p a of p, and thus you have here the minus. Okay, so now we did this adjoint action calculation. Okay, there are many ways to calculate it. This is the most brute force sort of physical physicist way to do it. You can also solve a differential equation to calculate this thing. And now we have this as a result of this adjoint action. And now we integrate over the spectral measure, which basically makes this small p into to the operator p that we were looking at. And you see now, this is the same as the commutative Minkowski quantum field theory. So that means I take an operator a of p, I deform it using these warp convolutions, using the momentum operator to generate the unitary functions. And by doing so, I obtain what Harald Grosse and Gandalf Lechner obtained by taking the unitary operator that maps you from non-commutative Minkowski space quantum field theory to this usual quantum field theory. Okay, so that means I don't need all what I learned before. All I need to do is take the things and do a warp convolution with it. Now, to give you a sort of so because last time I mentioned this warp convolution, and there's an integral representation of the star product. So how is this warp convolution depend on the Riefel product and on the star product? Basically, the integral representation of the star product is given by this one, okay, which can be understood as a translation of x, of f of x, with respect to the vector u, and the translation of g with respect to the vector v. And the thing about, so these are, so you have the algebra, which is, the algebra of C infinity functions over a manifold. And okay, and this is of course well defined in R if f and g are elements of the Schwarz space, or if they are continuous and all the derivatives are continuous and in a sense bounded. And what Riefel did is, and I'm very sorry to do this very short here, but he generalized it to a C-star algebra. Okay, so he generalized this star product, the C-star algebra, and applied it to many examples, like the plane, the cylinder, and the torus. So you have the quantum plane, the quantum cylinder, and the quantum torus. And now instead of taking, functions of the algebra, you just take elements of the algebra itself, C-star algebra elements, and then you define a corresponding norm for it, and so on. And the point is that, so if theta is a skew-symmetric matrix again, and you do a warp convolutions of A, you do a warp convolution of B, and you multiply those two, it is equal to the deformation or the Riefel product of A and B, and this whole thing warp convoluted. So, and where, this theta is, this x theta is the Riefel product on C infinity. So in a sense, what does it mean? The warp convolutions supply a representation of the Riefel deformation. It means So if this is the warp convolutions, P theta of A, P theta of B is equal to P theta of A cross theta B phi, okay? Now, the question that I ask myself is, what can we do with warp convolutions? And so warp convolutions, what are they good for, okay? And what are they physically useful for? And this is the question that I answered by basically spending most of my PhD on it, and to that I will come right now. So let me just okay. First of all, I asked myself, okay, now these I mean, for certain examples we know it, but what is if now forget all that I said. Now you take an operator A that is an unbounded operator, and you deform that operator. In what sense does it make sense still? Because in physics, we need self-adjoint operators. So let's say I start with a self-adjoint operator, a random self-adjoint operator, and I do a deformation via these warped convolutions of this operator. When is it well defined? And what came out is that if basically this u of theta x a u of theta minus theta x, so the adjoint action with respect to this unitary operator, is bounded in a sense, you have a well-defined oscillatory integral. And moreover, if you have a well-defined oscillatory integral, which means that the deformation makes sense, it turns out that this is an essential self-adjoint operator. Okay, so you have an essential self-adjoint operator, you do a crazy deformation quantization with it, and it's still essentially self-adjoint. And the reason, therefore, is the Cato-Rayleigh theory. And well, I don't want to get into it, but basically, I mean, what came to me one day is that A theta is nothing else than, you know, the undeformed operator plus something, and you know, this plus something is sort of the issue. And if I know this is self-adjoint, then I can, and this is symmetric, then there is the so-called Cato-Rayleigh theorem that can tell you under which conditions this whole thing is self-adjoint. And it worked, okay? So this is one of the works that I did there. And before I applied it to the most simple system that I had, which is basically quantum mechanics, right? So you have the free Hamiltonian, which is H0 is minus Pj divided by 2m. This is the plus operator. And the scalar product is bounded. So there's this bound there, and therefore the oscillatory integral is well defined. And if I insert for this unitary operator the coordinate operator, or a function of the coordinate operator, what happened is that from this free thing, so this pi squared divided by 2m, I obtained a minimal substitution, or we call it in physics a minimal substitution. This is basically a gauge field. Okay, so first of all, you take the free Hamiltonian, you insert it into this warp convolutions, and at the end of the day, you get a gauge field out of that. So the warp convolutions can be understood as a generator of gauge fields. And you can basically play that game for magnetic fields and gravitomagnetic fields. Gravitomagnetism is basically you take the Einstein equations and you take it for a slowly moving, slowly rotating, very large mass. And then the Einstein equations basically behave very similar to magnetic equations. Thus, we call them the gravitomagnetic equations. And you can, and then basically all I did was choose the operator I deform with, or choose the operator you want to deform, choose the operator you want to deform with, and choose these thetas, these Q-symmetric matrices, identify them with physical constants. By taking those three together, I was able to obtain a Zeeman effect, which is a very important effect when it comes to astrophysics, the Aharonov-Bohm effect, which is also an important effect, and the Lense-Thirring effect. And basically, you can formulate all quantum mechanics coupled to electromagnetism by using this deformation procedure. Now, I mean, so in a sense, I was pleased because physically, you know, it gave me something meaningful. So now the question was, okay, how far does it get us to our goal in quantum gravity? And this is still subject of research. I still haven't answered that question fully. So as I told you last time, I was thinking out loud, in a sense, sensible requirements or axioms for theory of quantum gravity. In quantum gravity, in my opinion, the metric should be operator valued. Furthermore, the flat metric should be given from the start. That I learned from the failures of others. And gravity has to be an emergent phenomenon. So in a sense, it should come by some procedure rather than putting it in by hand. And this procedure in my case will be the deformation quantization. And also one of my motivations was to obtain the Moyal-Weil spacetime as a solution. So in a sense, you put you don't put that much in, and you should get a lot more out. That was sort of. And I told you last time about this universal differential algebra form, so I don't want to go too much into detail. It is defined basically as a graded differential algebra. A0 of A is A, and the space of one forms are generated by this operator D that is nilpotent and satisfies the Leibniz rule. And then you define the P space of these forms by just juxtaposition of these one forms. And now let's start with a commutative algebra, AC, that is generated by the commutator of x nu and x nu equal to 0. So I don't want to start with a non-commutative one. I start with a commutative one, and out of that, I want to obtain, my Moyal-Weil spacetime. So by applying the operator D on the commutator relations, okay, I apply here a D, this splits in dx mu, comma x nu, plus x mu dx nu. And this is still 0.
Sorry?
Yes?
May I interrupt you for a second? I don't know if it's just me, but I cannot see what you're writing. I just see your pen moving, but...
All right. That is a good remark. Wait a second. Do you see it now?
No.
Okay, let me stop sharing and I'll share the screen again. Maybe then things get better. Do you see it now?
Yeah.
Perfect. No, did you say no or yes?
Yes.
Perfect. Okay.
Thanks.
You're welcome. Still see it? Okay.
Yeah.
Okay.
Yeah.
So I apply D on this commutator, as I said, and then one solution is I get C mu nu sigma, where C is symmetric in the first two indices, such that this is equal to 0 then. And since this is an algebra, differential algebra, and I also wanted to fulfill the Jacobi equations. So in order for this algebra to be a consistent differential algebra, I make a choice, okay? The choice of C mu nu to be A nu delta mu nu x nu. So where here there is no sum over mu and nu, by the way. That's why I wrote them in this upstairs case. Then a faithful star representation of this, commutative algebra denoted by pi is given on a dense domain, which is the Schwarz space, by the following one. A mu, this constant, half q mu plus 1, p mu plus 1, plus p mu plus 1, q mu plus 1, where q, I, and p, j sort of are delta I, j, I times h bar, where h bar is equal to 0. So they're the usual, they're the usual, Heisenberg relations or Heisenberg operators. And now I chose a representation of the universal differential as a derivation, okay? The best derivation there is, it's a commutator, okay? So you can, basically I represented the x, the elements of the algebra by this operators, and the representation of the differential of that by just taking the commutator with the representation of x. It obeys Leibniz and it satisfies d squared x mu is equal to 0 due to the symmetry. And then I deformed the flat spacetime. Okay, I wrote a flat spacetime, Minkowski spacetime, since I told you this is one of my axioms, as dx mu, dx nu. I generated those from this commutative algebra applying the differential calculus, and eta mu nu is just the one matrix. So I just, write that in there. And now I deform it by using unitary operators, which are basically e to the IP mu, p of x hat mu. And now I call them just x mu so that I don't have to write the pi all the time. So pi of x mu is big X mu, and pi of dx hat mu is dx mu. And now what is the outcome? So I put this line element eta mu nu dx mu tensor dx nu. Sorry, now because if I want to do a deformation, I have to work with operators on a Hilbert space. I cannot just work with abstract objects. And thus I represent them now by operators. And now the warp convoluted line element is given by the same formula of this warp convolution that corresponds in a certain way to the Riefel deformation. And what I obtained is the interesting thing. The representation of the differential algebra, we obtain a deformed differential operator e to the minus 2a mu theta x mu. Now, right, so basically what happens is the following. I define a flat spacetime, right? Dx mu, eta mu nu, dx mu tensor dx nu. And now I deform this guy. What happens is it's, since this is just a one, the deformation doesn't see it, I deform the objects here, right, the differentials. Whatever outcome I have out of these differentials, I pull, to this eta. And basically what happened is I went from flat to a curved spacetime metric, where the spacetime metric is sort of a conformal. So this is what one calls a conformally flat spacetime. And now, okay, now I do the same game as the one I did when I did it for the quantum mechanics exercise. I choose the parameters in a certain way, and then I get a deformed Friedmann-Robertson-Walker spacetime. So this is the normal Friedmann-Robertson-Walker spacetime. This is a spacetime that basically describes cosmology. It describes either the expansion of the universe. I mean, it describes the universe at certain stages. There are many stages. There's the matter dominant, the radiation dominant one. And right, and so in a sense, I obtained a deformed Robertson-Walker metric, and this even has a physical meaning. So I took this and I calculated the Einstein equations for that, and it had a physical meaning, but I will not get into that. What is interesting about this? So I obtained, the old stuff. I obtained some new stuff, and keep in mind that all these metrics and all this is still formulated in an algebraic operator language. So the quantization is in a sense already done, okay? And what is interesting is there is a certain demand, so in non-commutative geometry, especially when it comes to calculating not the differential forms, but basically generalizing the differential geometry framework to a non-commutative algebraic framework, we obtained, people obtained the centrality demand, okay? Which is basically you want the metric tensor to be central, which means it should commute with all the elements of the algebra. And that has certain meanings that I don't want to get into, but it basically means that the elements of the algebra have to commute with the metric tensor. And out of that condition of centrality and my deformed metric, I obtained the following theorem. Let the deformation matrix be given in a certain way. Then for all metrics that are obtained by deformation, the centrality condition is fulfilled by assuming the non-commutativity given by the Moyal biplane. So in a sense, I obtained the Moyal biplane, as a constraint, as a solution to my deformed setting. And that is it. Thank you very much for your attention and for your attendance. Yeah, any questions?
I have a question.
Yes.
So, for instance, you basically with deformation quantization, you can get like the gauge theory for electromagnetism. Can you generalize this to non-abelian interactions as well?
Very good question. I devoted 1 year to that, and almost non-abelian. I can tell you yes, but to non-abelian, no. I mean, I haven't found a way to do it in a good way because there is problems with the algebras. I mean, they're non-abelian, and thus you have a little bit of problems there. I published a paper which was called Strict Almost Non-Abelian Deformations, and I actually have a paper on my shelf about doing this warp convolutions, not with actions of Rn, but with actions of the Heisenberg group. So this is a a group that is non-commutative. I mean, R is a commutative group since U of A times U of B is U of A plus B. I can do it with the Heisenberg group, but not with non-abelian. Unfortunately, it hasn't worked.
I see. Okay, and I have another question, if I may. So let's say like you obtained Zeeman effect, gravito-magnetic field, basically weak coupling on quantum mechanics, right?
Yes.
So you start with free. Can you deform like starting in quantum field theory, like something like in the spirit of what cons do, that you start with, let's say in your case would be with a deformed action, like something that would be analogous to Kahn's spectral action, and then all of a sudden you get the, the quantum field theory, quantum electrodynamics by deformation?
That would be great. I mean, that's why I tried to formulate these non-abelian deformations, because that's exactly what I had in mind. But up to now, no. And to tell you the truth, I mean, there's a lot of work done there. Well, not in I mean, what they do is they take the usual Lagrangians of these theories and they put a star product everywhere, and then they, calculate themselves half to death, and they put on the renormalization of that, and then they do it order by order. That I'm excluding now explicitly the model of Vulkenhaar-Grosse, which is, a very rigorous model towards constructive quantum field theory of phi to the 4 in 4 dimensions. But I mean, the ansatz of Kohn to do it that way, it has in the strict sense of what convolutions of deformation quantization has not been done, but it's an open problem. I mean, it would be great if someone could calculate that. Right.
I see. Thank you very much for the talk.
You're welcome. Any other questions so far? Well, if not, then I thank you all for your attendance again. And yeah, I wish you all the best. See you.